So yeah, today I'll be talking about some context and some practical specifics about how we built stronger consistency guarantees into our existing key value store at Twitter. My name is Boaz. I'm on the core storage team at Twitter. We're one of the teams that provides, as a managed service, storage to the engineers at the company who are building their applications. I'll give you a second to follow me on Twitter. One of the ways that we do that, and I've been doing that for a while now, is with a database that we call Manhattan. It is our distributed key value store. It is the primary key value store at Twitter that we built from the ground up. About 4 years ago, Manhattan didn't exist. And today it is the canonical store for a lot of very important data at the company. Things like tweets, DMs, advertiser data, and a whole long tail of other applications. I'll give you some context about the database. Among other reasons, one of the things that we built Manhattan for was to be very easy for developers to adopt storage and get into production quickly with their services. In order to do that, we emphasize a few things. We provide self-service access to the database through a web interface. We try to hide as many infrastructure complexities as we can from our customers, the other engineers at Twitter. Things like making transparent global replication across all of the regions of our data centers. We allow customers to share space on large clusters. This reduces the provisioning time when you ask for storage, and it reduces the burden on the developers from having to set up and manage new clusters whenever someone has a new use case. And also we provide some nifty automatic visibility and observability and alerting so that people have visibility into how they're using the database. Now, like with any successful service, as it gets more popular and gets more adoption, people get used to using it, and they want to start using it for use cases for which it wasn't exactly designed. In our case, that could mean that someone who was using this eventually consistent key value store wants to start using it for parts of their data that need stronger consistency guarantees. When they try to do this, and they can't with our system, it causes a lot of pain. It means that they have to make trade-offs that they don't want to make or that they're not happy with. And either they make those trade-offs through using our system or through using a different system like in our DBMS that doesn't provide some of the guarantees that we provide. So you, as an engineer whose job it is to solve these problems for your customers, are presented with a choice that we see a lot, which is, do you build a new service or use an existing new service alongside in parallel to the service that you already have to solve these problems, or do you build new features into the existing service today? Now, this is a scale, and I don't need to tell you that you don't want to be on the far side of the scale where you build bloated software that's not very good at anything. But also, when you're building infrastructure, you don't always want to build services that are just too specific. And there's a few reasons for that. One is running multiple systems in production can be really painful. Every system is going to have a different operational profile. Every system is going to have its own little quirks, and it's going to be painful for your on-call engineers to know every system in depth. Another is that for complex infrastructure, a lot of things are going to be common between these services. For a database, for instance, you're always going to need to manage your nodes. You're always going to need to move data around. And you're going to have to either rebuild these components for different systems or try to continuously abstract components out of your systems, which can have diminishing returns. And probably the biggest reason that you don't want lots of separate systems is that I guarantee you that your customers do not want to talk to 5 different databases with 5 different APIs, each one that provides a slightly different guarantee or feature. So in reality, you want to be somewhere here on the scale, where you're building specialized systems that are good at what they do, but they can evolve in a logical and thoughtful way to provide more functionality to your customers. So that's what we wanted to do to solve this problem for our customers and the engineers at Twitter. And in order to talk about how we did that, I'll give you guys an overview of the architecture of our eventually consistent database. I'm going to go pretty quickly over a lot of general concepts. If you are familiar with distributed systems or with distributed databases, a lot of this is going to look very familiar. But if not, feel free to ask questions after the talk or find me at the conference. As good a place to start as any with the database is with the data model. Manhattan, as I said, is a key value store. And we split our keys into two components, a partition key, or P key, and a local key, or L key. Local keys are stored together on the same machine underneath a partition key. They have locality, that's why we call them that. And that means that you can do interesting range type queries. For instance, in this data set, if the P key is a user ID, you can say something like, get me all of the L keys that start with the word profile for this particular user, and you would get the user's profile. This should look familiar to you if you've used Cassandra or Bigtable as a row and column scheme, or if you've used DynamoDB as a hash key and range key. So we take these keys and we distribute them around the cluster. The way we do this is by hashing the partitioning key, placing it into randomly into a shard, and then replicating those shards and distributing them to the nodes in the cluster. When you want to make a request, a client sends their request to one of many stateless symmetrical coordinator nodes. Those nodes take the request, take the key from it, find the shard that that key belongs to, find the storage nodes that that shard lives on, and then forwards those requests in parallel to all of those storage nodes, waiting for a response. That response could be a success if it's a write. It could be the latest value if it's a read. Now, when I say that the coordinator nodes forward this data in parallel to all of these storage nodes, that should be a giveaway immediately that I'm talking about a quorum-based eventually consistent system. Specifically in this case, we use Dynamo-style eventual consistency, as in the Amazon Dynamo paper, and we have last write wins conflict resolution. By doing this, we can forward the requests in parallel to all of the hosts, and those requests can succeed and fail independently of each other without necessarily affecting the overall success of the entire request. And as long as you are making requests to a quorum of hosts, if that's important to you, in this case that would be 2 out of 3, and those requests succeed, you're guaranteed to get certain consistency levels, such as read your own writes in this case. So if these are writes to the database and one of them fails because of a network partition or because of a rolling restart, and subsequently you do a read from a database, and the read also succeeds against a quorum of hosts, even if one of those hosts previously failed, you're guaranteed to see at least one version of the data that is the latest version that you had written. And of course, we can't call it eventual consistency if we don't eventually make the data consistent across hosts. So we have an anti-entropy process that runs in the background called replica reconciliation. This goes and compares the shards across every replica, making sure that they have the same data, and if they don't, it copies that data over. So these are all some pretty standard, straightforward concepts. Why would we choose to build a system this way? The primary benefit that you get from building a system like this is super high availability. Because all of the storage nodes are equal to each other, we don't have a mastership relationship, we don't have latency and availability hiccups from things like failover and master reelection. And because we chose to send the request in parallel to all of these hosts, this is a latency throughput trade-off, you're essentially waiting for a best of n responses from these replicas, and you're getting the best possible latency that the system can provide at any time. And you also get simplicity.
And the simplicity is in exchange for maybe a slightly less than intuitive consistency model. You get last right wins, or really with any kind of hands-off conflict resolution, a way to transparently move data, asynchronously replicate data from one set of hosts to another, and have that data be seamlessly integrated into the existing data in the system. So if I copy data over through replica reconciliation, or if I replicate data over from a different region, that just combines with the data that's already on the system in a way that makes our cross-region replication story very nice and very easy for people to use, and you don't have to think about how my cross-region data is working in the database. But as I said, for some people, it's not quite enough. When is it not enough? One use case is much like in any other kind of concurrent programming, when you need a uniqueness or check and set constraint in the face of concurrent updates to the database. So an example of that could be if two users are trying to both reserve a username. Not only do I need only one of these users to ultimately succeed in reserving this username, I can't have races that result in both of them thinking that they succeeded in reserving the username, because this can break the business logic of your application. So for instance, if both of these users tried to reserve, they both saw that the username was free, they both said, assign it to me. If they both got a success on that assignment, but only the second person who happened to make that request succeeded, this is very awkward behavior for your application to have to overcome. And it also applies across regions globally. So two people might be trying to reserve a username. One of them is in Chicago, one of them is in Nairobi. Even if they're talking to different data centers, they should still get these same guarantees. And in the same example, you want one other thing, which is atomicity of your updates. If I send an update to the database to reserve this username, in the case of failure, I want it to fail everywhere. In the case of success, I want it to succeed everywhere. I can't get into a state in a failure scenario where a minority of hosts think that a username is reserved, and I can't guarantee a predictable read when I go back and try to see who has this username. This is a state that you can get into with eventual consistency, and that state will be resolved either in one direction or the other, depending on whether this existing host dies or not. So it's unacceptable for some use cases. So now we know that we have this kind of genuine need for a stronger consistency model. How do we adapt our current architecture in order to support this? We can add a new component into our request path, which is logs, specifically sequential, replicated, distributed logs. In the form, for us, of Twitter distributed log, which is a recently open sourced log library built on top of Apache Bookkeeper. The purpose of a sequential log is that all of the updates that go into this system, into this log, are able to be read in the same order by all consumers on the way out. It gets complicated when you replicate this log for durability, and you distribute this log for resilience and scalability. And the log has to deal with concepts like consensus or mastership with failover and fencing. And it has to get all these complicated concepts right. Now, this kind of component is becoming more and more popular in lots of different kinds of infrastructure. If you were at the last talk here, then you saw Kafka, which is one type of distributed log. And so I won't talk about how these logs are implemented, but I will talk about how we use this log. What are some of the complexities of interaction when we introduce this new kind of component into our request path and have this new kind of consistency model? So I said earlier that all of the keys are partitioned into shards. This shard is this ultimate granular unit of partitioning and distribution in the system. So we can move shards around in between hosts. What I can choose to do is say that all operations that are going to update or act on a shard have to go through a log. And I can make this log per shard infrastructure. And then I can have all the storage nodes that own this shard consume all of their updates for that shard from the log. And I have this guarantee that all of those updates will be guaranteed to be delivered and be delivered in order from the log. And now, once I have this, I can make these operations pretty much anything that I want them to be. They can be reads or writes, as they were before. Or I can start sending compare and set operations. I can start sending increment operations. I can send any kind of operation that is deterministic based on the data that arrives in the operation itself and the data that already exists in the database, which is guaranteed to be the same on every storage node at the time that that operation is processed. So we can already see that by introducing this, we can solve some of the problems that we were worried about before. Let's take the reservation example. I can model a reservation of a username as a check and set operation, where I say if a username is free, assign my user ID to that username. And two users who are concurrently making this request will appear in this log in some order. Which order doesn't really matter because they're doing it concurrently, and either order is valid. But what's important is that all of the storage nodes, all of the replicas that process this request see the same order. So what will end up happening is that the first one that enters the log will be able to reserve that username, and the second one will fail its check condition and not reserve the username and see a happy application level error. This kind of simple change to the messaging model allows our guarantees to be strengthened quite a bit. So let's zoom out a little bit and see how this fits into the larger architecture. Now when a client sends a request to a coordinator, instead of forwarding that request directly to the storage nodes, the coordinator forwards it to the log that owns the shard for which that key lives on. And then the storage nodes can consume from that log, play back the operation, and respond with, again, the success, if it's a write, the value, if it's a read, or whatever the result is of your more complex operation, back over to the coordinator. Now, if you notice, I have a new guarantee here that I didn't have before, which is that if the write enters the log, I know that the storage nodes will see it. And if a storage node processes an operation, I know that all the other storage nodes that process that operation will return the same response because they have the same data. So now I can start to do more interesting things with my request model so that I can keep the same guarantees that I want to have while lowering the latency on the client side for any given request. So for example, let's say I know for sure that all of my writes and all of my reads to my data set are going to go through this sequential log. Well, now I can say, if I'm sending a write, as soon as that write enters the log, I'm done. I know that that write will eventually be applied onto the storage nodes, so I only need to wait for the log to act that it has this write durable before I can return a success back to the client. And I know that any subsequent read will be queued behind that write in the log, therefore it will see the write as I expect it to. And when I send that read, or if I send a more complex operation that needs a result, I only need to wait for one of the storage nodes to respond, because I know that all the other storage nodes will respond with the same data. So this makes certain kinds of strong operations happen a little bit faster. We either get to wait for the log response or the fastest response from a host, but I can still do something interesting. I can say, I was waiting for a quorum of responses before, when in my eventually consistent model. How about I wait for a quorum of responses now?
So if I send a write, or if I send a CAS or an increment or something, I'll wait for a quorum of responses to come back. And if I do that, I know that that request is durable and consistent on the storage nodes themselves. And when I send a subsequent read, because I didn't change my request path, I only added a new option to the path that requests can take in this database. I can send a read through the normal eventually consistent fan-out path. And when I do that, I get all of the benefits that I was getting before from an eventually consistent request. High availability, low latency, without eating any of the cost of going through the log. But I still get to do updates in this more strongly consistent fashion. So this is an interesting model. And in a nutshell, this is how we can add this log component into the database to add stronger consistency. So let's see what are the results that come out of this. Well, first we've gained what it is that we were trying to gain. Because updates are ordered per shard, and keys are hashed randomly into shards, but consistently into shards, we've effectively gained in-order updates on a per-key basis, linearizability for our keys. Technically, we have in-order updates for everything in the shard, but because you as a user don't know for sure if any two keys will end up in the same shard, you don't really rely on that. It's important to note that we don't have full distributed transactions across shards. That's a more complex problem, and it's something that would have to be built on top of this more basic system. We also have, or we can say we kept, failure isolation at the shard level. Because all of our writes go through logs that are owned by shards, if we have a hiccup or an issue or a problem with an individual log, that problem is constrained to a very small sliver of the key space that belongs to that shard. And also, because we've only added this new path into our architecture instead of replacing it completely, we have this ability to do a couple things. Not only can we mix strong and eventually consistent data sets within the same cluster, we can actually, to some extent, mix strong and eventually consistent requests within the same data set. And this is what I mean when I say that we're providing flexible consistency levels. A user can move back and forth across this continuum between super high availability and pretty strong per object linearizability by just modifying the kind of request they make on a per request basis to the database. And that's really powerful for our customers and allows you to get exactly what you want out of the system at exactly the time that you want it. Of course, we made trade-offs. First trade-off is an obvious one. We've added a new component. It's not a particularly simple component into the request path. And so on average, we're going to add some amount of latency. In the local data center, that could be a few milliseconds of latency. If you're talking about doing coordination across regions, that is constrained by the disappointingly slow speed of light. And so you're going to have an order of magnitude more latency added to your requests that have to coordinate far across the globe. We've also, as much as we tried to isolate failures, exposed ourselves to this thing that we were trying to avoid, which is latency hiccups. So when there are some kind of problems or re-elections on an individual log that slow down the updates for an individual shard, a customer will see in their high percentile latencies an increase. And that has to be okay for you. That is a trade-off that you have to be okay with as an application developer. And finally, an interesting one. Because we said that all of these updates have to happen in order, and they have to be applied in order to maintain the integrity of the database and the data on the database, then we have this situation where if for some reason a replica cannot apply an operation that it reads from a stream, from a log, the only option that we have is to completely halt operations from that log. So why might we not be able to apply an operation? Normally everything should be applied, but
operating at scale, we have to take into account that there might be bugs. We have to take into account that there might be some kind of exceptional corruption issue. And that individual replica now cannot continue to process operations from that log, and we have a form of unavailability. This can be scary, it certainly sounds scary, and it's where things like excellent observability, excellent alerting, excellent tooling come into play to make sure that if this happens, because you have to account for all possibilities, we know about it immediately, and we resolve it as quickly as possible. So that's what it looks like when we add this new path in. And it's important, now that you have it, to think about how is this new model that we've added different from the existing model? And how do we use this new model and operate our clusters with this new model in a way that isn't special or unique, that just works with the system that we already had, so that for us and our customers, we're adding something without losing too much. So when I think about how this eventually consistent and this strongly consistent model are different, the first thing that comes to mind is where the authority of your data comes from. In the Dynamo-style eventually consistent model, the authority of your data is delivered alongside your values in the form of a version or timestamp. This version information is what's applied to the backend and decides if the new data can override the old data. So in this example, we have values. We have a key with value X at version 1 already on these nodes, and a new key is, the update to that key is coming in with value Y at version 2. And the only reason that update is accepted is because the version is newer. This is interesting because it effectively decouples the authority of data from the order in which that data comes in. It's what gives us that conflict resolution. It's because of the conflict resolution, it's what gives us the nice properties that we got before. It's what gives us the idempotence of the updates that go into the database. But it's interesting to reason about, even for the benefits that it provides. The new model is completely different. The order of the updates is all that matters for the data in the backends. And if I do want to keep around some version information, then I have to maintain that independently on every single host. And if I want that version information to be the same on across the hosts, which is something that I do want if I still want to be able to make those eventually consistent style quorum requests, then I have to do that as an implementation detail of how I maintain versions, because it's not an intrinsic property of the system that the data has versioning. And when I'm applying this data, I have to store it locally so that I know that I'm applying everything exactly once. I have to store where I am in the logs. So how does this manifest? One interesting thing that comes out of this is that because I have this guarantee that I will apply all of the data that comes in on the log in this order that it comes in, I have no more need for this replica reconciliation process. In fact, if I was to go and compare the data on shards and try to proactively correct the data that exists on the shards, I would be introducing more consistency issues than I would be solving because of the way the system works. So that's cool, but it also turns out that we still have a need for a very similar type of system that goes through and compares the data between hosts. Because when you have a cluster with terabytes upon terabytes of data in it, you have to constantly be checking for things like bit rot, for potential bugs, and potentially correcting them. So it's a savings, but not an enormous savings.
Another thing that changes is when you're doing data migrations. So at Twitter, like at most places, when we build a new system, we generally want to take advantage of the benefits that we built it for by migrating some services from the old systems that they were on onto the new system. And to do this for a database and to keep that service live and not have any downtime, what you generally do is send requests, especially write requests that are coming into that database, that are coming into the service to both databases. And then in the background, you backfill old information from the old database system to the new one. In an eventually consistent key value store with conflict resolution, this turns out to be pretty trivial to do. You simply send writes to both of these systems. You copy the data over however you want to copy it. The conflict resolution takes care of everything for you. When you're done copying, you can just switch your reads over to the new system. Pretty simple. For the more strongly consistent model, this is no longer the case. If I want to do something like move an application that was on MySQL or an RDBMS onto Manhattan, we might have operations running that rely on the data that exists in the system while also updating that data, things like compare and set. So I have to write extra code on a per application basis to make sure that the data is populated correctly between the two systems and that we maintain integrity and correctness. A change that we had to make in the same vein is to the process of how we add and remove nodes from the cluster, which is something that we call a topology transition. So again, an eventually consistent system, doing a topology transition, moving a shard from an old set of hosts to a new set of hosts is pretty easy. You start directing writes that belong on that shard to the new replica set, as well as the old one. You snapshot the data, you copy it over. When it's done being copied over, you move all of the writes and reads to the new replica set. Because order doesn't matter, this works out on its own. But with the more strongly consistent model, you have to think a little bit harder. Because you can't just start sending writes to the new set of hosts, you have to change the topology state machine, the transition state machine that manages the addition of hosts to accommodate these new components. So the first thing you do now is say, instead of accepting writes, just say, I have a new set of replicas in the cluster, and I care about the updates that are coming in off of this log for this shard. So at the very least, don't delete them from the log before I have a chance to read them. Then you snapshot the data and copy it over as normal. And then you add this new state to the state machine, which for eventually consistent data is a no-op. But for strongly consistent data that reads from a log, says, give me a chance to catch up all of the updates that I missed from the log from the point where I got the snapshot. You need to do this catch up before you start accepting requests. Otherwise, as soon as you start accepting requests from these hosts and saying that they're trying to listen for the responses that these hosts send back to the coordinator, you suddenly will be taking a request that was taking 10 milliseconds and making it take multiple minutes or however long it takes for these nodes to catch up to the current state on the log. One last change that we made was in how we implemented TTLs. So a TTL, or a time to live, is a really useful feature where you can indicate that a value should no longer be readable after a certain point in time. You might use a TTL because you're collecting some kind of user data and it's not relevant anymore after a few days, so you don't want to be able to read it, you want it to get cleaned up. You might use it because a user is active for 30 days or something. So you want to, when the user logs in, you'll say, this user is active, set the TTL for 30 days. Automatically after 30 days, the user won't look active anymore. if they haven't logged in again. So in the eventually consistent model, it's implemented in a pretty straightforward way. If you read a piece of data from a node and that node thinks that that piece of data has expired, it simply doesn't return it to you. This is going to be subject to the normal amount of clock skew that happens across nodes in a data center. But it turns out that for our eventually consistent model, that's okay. It doesn't break anything. Everything still works as you expect it to work. But of course, for a strongly consistent model, it's no longer okay, because the expiration of this data is a data manipulating event just like any other. And we know that all of these such events have to happen in the same order. So you can imagine relying on the clock of the node and these nodes having clock skew and doing something like a check and set operation. And if on some nodes you're doing a check and set operation against a value that exists, and on some nodes you're doing it against a value that the node thinks doesn't exist, you've now introduced a divergence into your data. You have an inconsistency between your replicas, and this is exactly the case that we were trying to avoid. So in order to get around that, we decided to no longer trust an individual node's concept of the time. Instead of relying on the node's clock, we send, with every operation, a timestamp indicating what time the node should think it is. We can do this because our distributed log architecture allows a single master, a single writer for every log. And so we can ensure that this concept of time, that this clock, is always monotonically increasing. So when we send each operation, the node updates its concept of time, and now only across operation boundaries can data be expired due to TTL. And that way we guarantee that all of these things happen in the same order. It's a pretty interesting solution. It's a very popular use of our database, and it's not, generally TTLs is not something that you see in more strongly consistent systems. So one last thing I'll say is that at the beginning of the talk, we discussed what it is that the users of our database wanted. And in order to support what they wanted, we made all of these changes to the back end of the database. We introduced two quite differing consistency models living side by side. And the question is, did we succeed in adding functionality without disrupting the user's experience? So in order to use this new mode of the database, all a user has to do is, when provisioning the data set in the web UI, they choose a stronger consistency type. And when making a request through our client, they set a stronger consistency guarantee. Or if they're doing an operation that didn't exist before, like a compare and set, they can use a simple API for that. And not just that, if they try to do something that we don't think is safe to do against this data, for instance, if they send a request that is trying to update in a fan-out, eventually consistent way a data set that's strongly consistent, it's trying to send a write not through the replicated log, we inspect that request, we decide that it's not safe, and then we send back a very long but clear error message saying what it is they're trying to do, why that's not okay, and what they might do instead. And in this way, we maintain one of the most important things about this database that we were trying to achieve when we built it, which is that it's very usable and easy for people so that they can adopt quickly without bringing our team into the loop for most issues. Thank you very much.